Hey everybody, it's Patrick from Phoenix.com. In this video I'm going to show you how to use an FPGA, or field programmable gate array, to crack MD5 passwords. Basically, an FPGA allows you to prototype large digital circuits utilizing a hardware description language such as VHDL. The FPGA allowed me to create a large system dedicated to cracking MD5 passwords. The FPGA that I'm using is the Altera D2 development board with a Cyclone 2 chip. And with this board I was able to fit 16 parallel MD5 cracking units. Each unit is able to produce MD5 hash every 68 clock cycles. And since the board's clock rate is 50 megahertz, it's able to produce about 44 million MD5 hashes a minute. And basically how it works is you input your hash on the keyboard, and the system will try to brute force the password, and if it finds a match it'll tell you the clear text password on the screen. So let's go ahead and program the board here, and I'll show you how it works real quick. Alright, zoom into the screen here. Alright, as you can see, that FPGA is prompting you to put in an MD5 hash, and you just do that by typing hex values on the keyboard. And basically it's just a shift register that shifts in all the hex values. And then you can just push enter to run it, and it'll just go through all the combinations until it finds a match. Alright, there you go. I found the password. It's blah exclamation point. The character set that I use in this program is fairly large. It's 94 characters. It's basically every visible ASCII character. So it can take quite a while to crack large passwords. Alright, you just saw the MD5 cracker in action, and now I'm going to show you how it works. Like I said earlier, I used VHDL to design this project. And there's several components to it. There's a keyboard unit that will take input from the user, 16 independent MD5 cracking units, each of which is capable of producing a hash in 68 clock cycles, and a VGA unit to display output to the user. Alright, I'm going to start off by explaining the keyboard unit. Alright, so basically it takes in the clock and reset from the FPGA. Clock goes at 50 megahertz, and then it takes the clock from the keyboard and also the data input from the keyboard. This is basically how a keyboard works. You got the two inputs, you got the clock and the data, and whenever a key is pressed it sends 11 bits of data. And basically the clock on the keyboard is a little dirty and slow. I have to divide the system clock so that way it's a little bit slower. And basically it goes into these 2D registers, and basically what this does is detects the falling edge of the keyboard clock cycle. And when it does detect that falling edge, it tells this keyboard register to shift in data from the data line. Alright. And basically, like I said, it sends 11 bits of data, and once it's finished with those 11 bits of data, the keyboard register tells the keyboard detector to analyze, to figure out what key was pressed. And basically the keyboard detector can detect keys 0 to 9 and A through F, which are hex values, and it also can detect backspaces and enter key. So basically whenever you press a key corresponding to a hex value, it is shift into the user hash register, and if you push backspace, it's shift in the opposite direction, basically shifting out the last key you pressed. And then whenever you push enter, it turns the run signal high, and it tells the cracking units to start brute forcing the password. Alright, and as you can see, the outputs of the keyboard unit are user hash and run, and those are connected into the MD5 units and the VGA unit. Alright. There are 16 different cracking units, so I have an input adder number, which basically specifies which cracking unit it is. And the reason why I need this I'll explain later. So let's go into the MD5 cracking unit. It consists of a brute force unit, a register that holds the current password string, it has the MD5 unit which calculates the MD5 hash, and it has some other units to set up and compare the hash with the user hash. Alright, so let's look at the brute force unit. Inside the brute force unit there's 20 character adders, which basically are simple adders that when told to increment will basically add one to the previous character. The first adder is a little bit different than the rest. It has that adder number being inputted into it. So this basically specifies the subset of ASCII characters that it goes through. This way, every MD5 unit goes through a different, the first character goes through a different subset. This way, passwords aren't tried more than one time. And there's some other things in here that set up the way that the password needs to be padded and the way that it needs to be organized. Those are all technical details that are specific to the MD5 algorithm. If you're interested in that, you can read up on it. I don't want to go too much into it right now. And then there's other character adders which will go through the entire character set. And basically the character set is almost all clear text. It goes from exclamation point to tilde, and that's 94 characters, so it's quite large. And the reason why I chose to use all these character adders is because it only takes a single clock cycle to produce the next password that gets fed into the MD5 algorithm. The output of the brute force unit is input into a word reg, which basically holds on to that password until the MD5 unit is done computing the hash for that password. Alright, and you also see that there's a bus that comes out of the brute force unit that says active adders that basically tells, and that basically just specifies the length of the password, which is needed for the MD5 algorithm. And then, yeah, the output of the word register is put into the MD5 unit. And then the MD5 unit goes through the entire process of computing the hash, which is 64 steps. And I don't really want to go into much detail about the MD5 algorithm. If you are interested in how it works, just go to the wiki page and it explains it pretty well. Basically there's 4 stages, with each stage having 16 steps. Alright. Once the hash is done, it's fed into the setup hash, which basically rearranges it and puts it in the same format as the user hash so that they can be compared. And then if they match, the found output goes high, and basically this word setup unit holds the clear text password until that found signal goes high. The output of this unit will be high impedance. That's because it's outputted to a bus which is connected to each of the MD5 units, and you don't want multiple units driving a bus, so that's why it's high impedance. But as soon as that found signal goes high, it will output the clear text onto the bus. Alright, and that's pretty much it for the MD5 unit. And as you can see here, like I said, all those outputs, all those clear text passwords are connected to the bus, and all the found signals are connected to another bus, which feed into basically a large OR gate. So what happens here is, if they're all 0, then this signal over here will be 0, but if any one of them is 1, that signal will be 1 also. And the reason why I do this is because the first MD5 unit is a little bit different from the rest. It will continuously output its current clear text password, so that way you can keep track of which password is being tried. And basically that output is fed into a large mux, and as long as none of the MD5 units have found a match of the password hash, they'll be continuously inputted into the VGA and outputted on the screen. But as soon as one of the MD5 units finds a match and the found signal goes high, the output of that large mux will be the output of that MD5 unit, so that the password can be displayed to the user. Alright, the last unit is the VGA unit. It's kind of technical, so I don't want to go into it too much. Basically, we have a VGA controller which will control the horizontal sync, the vertical sync, and the VGA clock. And basically it will send X and Y coordinates to our other entity. It'll basically determine what needs to be displayed on the screen for that pixel. And there's several components inside the VGA color mapper. There's one for the hash, there's one for the clear text password, and there's one for just text on the screen. And basically, depending on which coordinate is being input into the VGA color mapper, will determine which one of these control units will be controlling that pixel. And if you're interested in learning a little bit more about how this project works, I will be posting all the code online so that you can download it and check it out. Alright, let's compile the code now. I'm going to time-lapse it here because it takes forever to compile this code. Alright, it's finally done compiling. After about 33 minutes, the code was finally compiled. And the reason why it takes so long is because it basically maxes out the entire board, and it has to spend a lot of time figuring out how it's going to fit onto the board. And as you can see here, it takes up about 95% of the entire FPGA chip. I basically try to fit as many MD5 cracking units on there as possible. Alright, now we're ready to program the board. The next thing I'm going to do is show you how fast the FPGA is compared to my computer. Now I'm going to show you how fast my FPGA MD5 cracker is compared to my Intel dual-core 2 GHz computer, by having a race to see which one can crack a password hash first. Alright, on my computer I'll be using Kane to crack the MD5 password hash. I'm just going to generate some random hash here using a whole bunch of symbols and stuff like that. And I'll just copy that into the cracker and Kane. Brute force. Make sure I use the identical character sets. Okay. And I'll just type that into the FPGA. And I'll start cracking at the same exact time. First open the clock here. Alright, the FPGA is done. It took about 3 minutes and 45 seconds to complete. Let's see how long it takes the computer to finish up. Alright, it's been about 10 minutes and 15 seconds, and the computer finally finished cracking it. It's quite a significant difference, and you can just imagine that as the password gets longer, the difference is just going to get greater. Well, that's pretty much it for this video. I will be posting the VHDL code online, so you can download it and try it on your own FPGA. Alright, see you later.